Just a sec. All right, we are live. Welcome everybody to this 38th and last Data Science Leuven meetup of the season. There is really not a lot of people watching, so it seems. Can you all, when you're seeing this, can you all let me know that you're there? Because it's really weird. I see 9 viewers. All right, 9 viewers. Let the view count go up as the talks go along, right? So I prepared a few slides to introduce the gentlemen here, but you can see their faces on your screen, right? But anyway, let me share my slides. Just a sec. Here it's coming. Of course, I didn't test sharing my own screen, so now if that doesn't work, then here we go. All right, so the 38th meetup is today. We have 3 speakers here. The first will be Quinn Lathrop. I hope I pronounced it correctly. You're head of data science at Data Camp, and the topic of your talk will be psychometrics and measurement in the context of predictions in ML. We decided with the 4 of us that would be the most academic talk of tonight, so that's why Quinn can go first. He even bragged about having 3 formulas on the slide, so let's see. Next up is Ashish. He has written, sorry, I see I made a typo here, like a copy-paste error, but Ashish will talk about mastering Pytorch. Is a book he's written himself, so it's pretty cool for all of you who want to know more about Pytorch. The master is right here, and he will show you what the book is about and what you can learn. And finally, we have Gaëtan Potvin. I'm not sure if I pronounced that correctly. Also from Data Camp, so it's a bit weird that we have 2 speakers from the same company in one night. Although in my defense, one is based in New York and one is somewhere here in Belgium. So that sets them apart. And the second reason why we do this is I guess in terms of data science capabilities in Leuven, Data Camp is our most well-known export product, right? But we're all proud of. So we're also very proud to have 2 people from Data Camp in this talk here today. And Gaëtan will talk about ViewFlow, which is a framework built on top of Airflow that enables the scientists to create materialized views. So I'm looking forward to all 3 talks. I think I will understand the last one. I hope I can follow along with the second one, and I hope I can get to slide number 2 on the first one. So with that being said, I'm going to stop sharing my screen. There we go. So yeah, I would say, Quinn, the floor is yours. You can start sharing your screen. Ashish and Gaëtan, I'm going to put you and myself back into the lobby, and then Quinn, the floor is all yours.
All right, thank you for that introduction. And can you confirm that you can see that the slide?
Yes, I can see it. Yeah.
Okay, great. Yeah. So my talk is going to be on psychometrics and measurement. My formal academic background is in psychometrics, and this is a topic that typically doesn't get a lot of attention in the broader ML space or just the broader data science space. It tends to be, or at least historically has been, fairly walled off, both in academia and in application. So what I wanted to do was to provide a very high-level overview, as well as some specific points of connection, both in the application and in the theory, to other methods that the audience might be more familiar with. So just again, to introduce myself, my name is Quinn Lathrop. I'm the head of data science and psychometrics at Data Camp. Please feel free to connect on LinkedIn and follow up. And I do hope that this is not my last Data Science Leuven meetup. I do hope that the next one will be in person so I can join you for beers afterwards. So, a high-level overview, what are some things that potentially you could gain from this? Well, one is, what is psychometrics? Second is, what do we mean when we say measurement? And are we talking about measurement as a metaphor or something more serious? After that, we'll talk a little bit about software used for IRT, which is a framework of models within psychometrics. And then specifically, there's some interesting connections between IRT and logistic regression that we'll dig into a little bit as well. So let's get the first one out of the way with just some definitions. What is psychometrics? Well, Wikipedia says it's the field of study concerned with the theory and technique of psychological measurement. Within psychometrics, there's a subfield called item response theory, abbreviated IRT, which focuses on how a person's response to a single item relates to the person's overall score or overall measurement on some underlying trait. Now, we use the term item to represent this thing that a person interacts with. The easiest way to think about it and the simplest explanation is that in say, a mathematics test, we might give a multiple choice question that says 2 + 2 = blank, and the user needs to produce evidence of a response to that. So they might select an item, and we use that response to make some claim about the underlying math ability of that user. And so even though we say item, oftentimes that's interchangeable with exercise or question, but that is with some loss of generality, because oftentimes an item can be much more complex. We can embed it into an interactive system or some intelligent system or a simulation, for example. So while the simplest case might be a multiple choice question, that is not necessarily a limitation. So what are some typical uses of IRT, just to ground the conversation? The first is high quality measurements of latent traits. And we'll get into what I mean by high quality. But if we think about being able to measure somebody's math ability, being able to measure somebody's skill level in Python coding, being able to measure some mental health trait, these are all non-physical traits of humans that we might have an interest in measuring, but they aren't directly observable. And the mental health example is one that's somewhat interesting, because if you think of other things in medicine, I can measure someone's blood pressure fairly accurately. I can measure their temperature with a thermometer. It is very difficult to measure somebody's level of depression. There is not a thermometer for depression. Instead, we develop scales that may be in the form of a questionnaire, for example, in order to compare, but first measure and then compare scores on some sort of latent trait like depression, similar to how we would like to compare, say, temperature in degrees of individuals. Second is we can use IRT to be the tool that evaluates our items themselves. And so if we continue the example of a scale that, or a questionnaire that measures depression, we might initially create that questionnaire by consulting with experts, then collect some data on that. And then using IRT, we can evaluate how well those items are working and improve the item creation process itself. There are several examples of measurement-based products, such as placement tests. So for example, entering into a university, especially in the US, there are many placement tests that are required. Certification tests would be another example. And they can be used as an intervention or a trigger for remediation in adaptive learning systems. Okay, so this is the one slide that has 3 equations on it that determine my place in the ordering tonight. But this is really the core of item response theory, and so I wanted to spend some time talking about it. First, starting with the graph, here we are visually representing 3 items, so 3 questions. The main thing that we're trying to do is to model the probability of a correct response as a function of an underlying ability or a latent ability. And so we could take this, for example, as 3 math questions. And as somebody has more math ability, they have a higher chance to get those questions correct. If we look over briefly at the equations, the data that we get are 0s and 1s, and we model the probability that the answer will be a 0 or a 1, correct or incorrect, of the item response. We generally do that with some sort of parametric form, which this form is indicative of a logistic parametric form. And then we get to the key element of item response theory, which is that we have, in this simplistic model, a single parameter for the person and a single parameter for the item. The theta parameter is often interpreted as the user's ability, and the beta parameter is the item's difficulty. So to see how these difficulties are interpreted, they are interpreted as the point at which, or the amount, the level of ability required to have a 50% chance to get the item right. And so, for example, this red item is the easiest because on the ability scale, its difficulty is down here. The black is in the middle, and the blue is about here. What this means is if my ability level is 0 on this latent scale of math, I would have a 50% chance to get this black question right. I would have about a 90% chance to get the red question right, and I would have about a 25% chance to get a blue question right. The key point here is that as I move up in ability level or as I move down in ability level, the thing that changes the probability is my distance from the item itself. What this does is it allows IRT to place the item's difficulty on the same scale as the person's ability. So we can create these what are called item maps, where we can align basically the sample of users that have interacted with the test with the items that were used to create the test. And this being able to do this is important for what it means for measurement. There's the transition I was looking for. So what is measurement? So if you ask just a typical person in social sciences to define measurement, they might give an answer which describes measurement as a metaphor, which is, well, we assign numbers to objects or events according to some rules. A physical science definition, which is a bit more strict, is that we are estimating the ratio of a magnitude to a unit. And so when we describe measurement, what are we talking about with IRT? Well, if something is measurable or is quantitatively measurable, is often a testable assumption. And for example, there's one axiom called additive conjoint measurement, where if z equals x plus y can satisfy certain axioms, then all three variables, x, y, and z, have a quantitative structure. So when we think about item response theory, we can test whether or not the data fit, and under certain conditions and under certain models, if the data fit, the model produces a quantitative latent trait. This means that the latent trait can be measured at an interval level. And this is, I think, one of the key points that I would like you to walk away from the talk with. That when we talk about measurement in item response theory, we are talking about interval level measurement, not a metaphor. And so when we describe the level of math ability on a latent trait, we are trying to create a ruler to measure math and then apply that ruler onto the latent traits of the individuals that have taken the questionnaire or the test. All right, so now moving away from more of the philosophy of measurement, and I want to talk about two things. One, the optimization problem, what are we trying to do? And then how measurement relates to predictions. So typically for item response theory, we have data that arrives as zeros and ones for correct and incorrect responses. This can show up in a few different ways depending on what you're most familiar with in your background. It can be a wide data set or a matrix where the columns identify the items and the rows identify the people. It could also be formatted in a long way where you have a column for the item identifier, a column for the person identifier, and then a column for the correctness of that item-person interaction. As we talked about before, we typically assume a logistic parametric form, and often we want to optimize the parameters so that they maximize the Bernoulli likelihood, which is the same as minimizing the cross-entropy loss. So for those familiar with logistic regression, this feels a lot like logistic regression. So the question would be, why can't we just use logistic regression for this problem? And the answer is that there are no X's. The X's of a typical logistic regression formula are our latent traits. And so if you formulate logistic regression as this y-intercept slope x, from just the y's, the task is to estimate the intercept, the slope, and the x. Item response theory creates the x's. That's the measurement of the latent trait and the primary outcome of the analysis. Predictions themselves are not as important. IRT focuses much more about the measurement of latent traits and the item quality, but typically doesn't care about making future predictions as much. Okay, so then if we were doing a logistic regression and we were all in person, I could ask you, what are the packages or the software that you would use to estimate logistic regression? And we could come up with several general purpose software or widely used packages that we could use to estimate a logistic regression model. Item response theory is not so similar in that way, in that if you Googled software for item response theory, you would probably get a list of very specific software that have names like this. Now, oftentimes, these are proprietary, and not open source, so you need to pay money for them and licenses for them. And they tend to be graphical user interfaces, so you can run an analysis, but it's difficult to build software or applications on top of those models. Well, I think, especially in my education, that these softwares and the separation from just general purpose modeling or optimization packages was one reason, or potentially one reason, why psychometrics is a little bit walled off from the rest of the world. But I would like to propose that it doesn't need to be that way, and I'm certainly not the first, so I'm reviewing more of how I view item response theory. The first way is that we can formulate item response theory as a multi-level model. So if you're familiar with multi-level model or hierarchical models or random effects models, we can treat a latent trait as a random effect. So for example, if you're familiar with LME4, the model specification looks like this, where we have no intercept, we have a fixed effect for the item ID, and then a random effect for the person trait. What's fascinating about this is this now makes it just a regression problem, and you can do everything else that you would like to do in a normal regression problem. So in a multi-level framework, I may want to treat the items as random effects. If I have students nested inside of classrooms, I might want to build a 3-level model and have students nested inside of classrooms. And approaching item response theory in this multi-level framework allows us to do that. We could also approach item response theory in a Bayesian framework. So here's an example of the exact same model, but in a stand syntax. If you're familiar with one or the others, don't worry. I'm just trying to provide enough bait to get you interested. But here again, we solve the problem of not having the x's in logistic regression by specifying a normal 0-1 prior over theta. And that's how we solve that estimation issue. We can also do IRT in Tensorflow, or as we'll see in the next talk, Pytorch can also be used by using embeddings. In this case, what we're doing is setting up a one-dimensional embedding for the items and a one-dimensional embedding for the user ability or the person ability. Combine those together and activate it with a sigmoid, and you can do this as well. What's fascinating about using something like Tensorflow is if you have extra data, for example, you are collecting these responses in an online learning platform, we generate so much more data than just zeros and ones from the item response. We know much more about the user's session. We know how much time they spent. We know their location. We know what they've done in the past. We know probably something about their intention. All of that can be fed into this model in different ways that a traditional approach to IRT cannot provide out of the box. So then finally, in the last few minutes, I wanted to talk about some connections to machine learning and specifically to predictions. So if we think about many machine learning products, especially in the recommendation and the personalization space, these are based on predictions. So an online store might recommend a shirt that similar customers bought because they predict that because you are similar, you will buy it too. Netflix might recommend a movie that they predict you will watch or that you will explicitly rate highly. And similarly, personalization campaigns do their personalization because it is predicted to improve your click rate. So all of these examples are about predicting future events and then maximizing or building a product on that prediction. Adaptive tests that use item response theory, where the next item selected only comes about after a response is given, does not optimize to predict the future. Instead, it optimizes for measurement. And so if you're familiar with information approach to modeling, what we're trying to do is find the highest informative item that will reduce the standard error of measurement as much as possible. That will increase the efficiency of the test because in either a given time or a given number of items, the goal is to reduce this standard error as fast as possible. Now, that's not to say that measurement and prediction are two separate things. And I believe, and I've built products where they can coexist as shared outcomes that support product needs. So if we go back to this information approach where we are trying to maximize measurement, if you think about how you would maximize the information from a Bernoulli distribution, you would want to add a data point where that Bernoulli distribution crosses the 50% threshold. That will give you the most information about the location of the parameter you're trying to estimate. What that means for a product and a learning product is that we would expect users to get 50% of problems wrong. That may work for a high stakes test or a placement test where a user is paying and they have to. But if we are building a learning product or trying to increase engagement or trying to make the experience sticky, telling somebody they got a question wrong 50% of the time is likely not the most optimum experience. So I may, by optimizing for measurement, I may basically increase the efficiency of the test, but lose customers along the way. So instead, what can be done, for example, is pick a zone of proximal development where I would like a user to get, say, 70% of the items correct or 75%, and then within that window, pick the highest information item. And so measurement and prediction can coexist, and they can create a shared outcome to support product needs. So given where we're at with time, I will actually stop there and just say that the main goal of psychometrics is to measure a latent trait. The way that we do that is not necessarily only to use historical software or not necessarily to use historical methods. There are many ways to approach this problem, and I hope that this talk has piqued some of your interest. So thank you very much.
All right, thank you, Quinn, for the presentation on psychometrics. So let me check in the comments if there are a few comments already. As I said, like there is some delay between what is broadcast on YouTube and what is shown here. But maybe while we wait for comments from the audience, maybe let me ask you a question. So can you, I don't know if you can share this, right? But are you applying this within DataCamp, and if so, how are you applying this knowledge within DataCamp?
Oh, yes. So in DataCamp, where this is primarily used is in our assessments and our certification product. And so we use assessments to both inform learners how they are progressing along a career track, as well as in the B2B space, provide professional development admins feedback and measurements on how their employees are doing as they progress through their professional development experience. We have a certification product as well that right now it has a certification for data scientists that begins by taking and passing assessments. And so we use item response theory to both create those measurements and to ensure the quality of the product.
Got it. All right, thanks. There is a question from the audience in 3 parts, actually, from Lien, because she's struggling with typing on an iPad, but I'll read it out for you. So Lien asks, you showed a few Python code examples. I think it was R though, right? Was it Python?
There was, yeah. So it depends on your framework of choice. If you leave another comment, I can give you an exact reference. But if you're looking for vanilla Python, there are those. If you want to use Stan, so for example, PyStan or Edward, that's also a possibility. If you want to use TensorFlow through Python, that's also a possibility. R tends to have a little bit more, just in general, custom or specific packages for psychometrics, as it does for a lot of other things. But but there are many open source packages that exist depending on where you're at.
Yeah.
Okay.
Yeah,
cool. I'll post a few links in the comments.
All right. Cool. Thank you very much. If there are no further questions from the audience, then thanks, Quinn, for this great presentation. And then with that, I'll bring in the next speaker, which is Ashish. Quinn, I'll put you back in the lobby. Thanks a lot for your presentation, man.
Thank you.
All right. Hey, Ashish. So yeah, let me remove that banner. So you're going to talk about mastering Pytorch. I would say that the floor is yours. You're not sharing your screen yet, though, so I'm still waiting for that.
Thank you, Chris. I'm going to share it now. Can you see it now?
Yes, here it is. I'll remove myself as well. Yep.
Thank you so much. So yeah, hello everyone, and thanks once again, Chris and Data Science Leuven, to give me this opportunity to share not just my writing experience of this book, Mastering Pytorch, which I published in February 2021, but also to share with you few glimpses of what the book is about, and yeah, give you an example of how the exercises I have written in the book look like. So without wasting much time, I will go into it straight. So I'm not going to cover the details of the book, obviously, because I only have 20 minutes and that's something for the readers to read the book. But what I intend to cover in this presentation is a few things. First is the motivation, which is why I wrote this book, like why another deep learning or why another Pytorch book, and then the process. So for those who are interested in writing a machine learning or a technical book, just wanted to share what the process looks like. And then obviously a quick peek into the book, what it is about, what are the contents very briefly. And finally, I would like to wrap up the presentation with a live coding exercise, just to give a feel of how the exercises in the book are. So firstly, the motivation. So last year, I have been thinking about writing a deep learning book for a long time, but my inspiration comes mostly from this great book called Head First Java. So Head First is a series of books, and this one is about the Java programming language. The speciality of these books is they are incredibly illustrative. So even a layman can at least read them and get some sense out of them. So it's very relatable and very applied. And so I felt that kind of a book is missing, at least in the deep learning or machine learning paradigm. So this was my initial inspiration, and I had some conversations with the publisher Pact, and they wanted to write a Pytorch specifically book. So I used Pytorch as the medium of explaining deep learning in as applicable and as illustrative way as possible. But also besides head first Java, I would like to address the question on why yet another book, yet another deep learning book. So we all know we have a lot of literature already, and even I have read all of these books, at least some chapters, but I still felt some aspects were either missing or were a bit too much. So one of them, for example, was that the textbooks have a lot of advanced theory, which I personally did not need the knowledge of in my 6+ years of working. What I really needed more is applied knowledge. So that's something I wanted to emphasize in the book I wrote. And also I wanted to add the perspective of an engineer, of a machine learning engineer or a deep learning engineer. And by that I mean aspects such as productionizing a machine learning model, using machine learning in the cloud. And finally, in Pytorch, there is a very rich ecosystem of libraries. Think about Fast AI or Pytorch Lightning, which really facilitate a lot of advanced deep learning related work, which few people know about how to use them precisely. So I wanted to add that information as well in this repository. So these were like a few kind of pieces of inspiration or motivation for me to actually put together an all-together book for Pytorch. All right, so about the process of writing a technical book, I could look back and make out like a few steps. So it all begins with deciding a table of contents and agreeing with the publisher about the table of contents, and then you write a few words about each of the chapters that you have mentioned, so that you are sure you align with the publisher what you are going to write within those chapters. The most important bit after that is to agree on a schedule where each chapter has a precise deadline, and then you start writing the chapters sequentially. I used Google Docs as the tool for writing the chapters, nothing fancy. And when I was writing the chapters, basically I first wrote some scaffolding text, just the various subsections. Then I wrote some code for the exercises. It's very important to get that right. That's the most important part. To test them and also to push them to GitHub, and to create the diagrams for illustrations wherever applicable. And I used, again, a very simple open source website called draw.io for making the diagrams. And finally, just complete the entire chapter, like fill up the chapter text and make it concrete, and review the chapter again and again with the publisher at different levels, at the level of language, at the level of code, and then even higher levels such as editorial or category reviews. Category review here could be things like whether the topic really aligns with the initial concepts that were written in the briefs. So this, to me, like this is basically the life cycle of writing a technical book. All right, so like apart from the motivation and the process, what exactly this book is about. Firstly, this book is 450 odd pages long, split across 14 chapters, which are further split in 4 sections. And the 4 sections are like the following. So you have the overview of PyTorch, the deep learning framework. And when we say deep learning framework, it's kind of necessary to also remind about deep learning again. So that's the idea of the first section. Then there is an emphasis on some advanced neural architectures in the second section to go deeper into the actual knowledge base. The third section is really mostly focused on applied, basically deep learning applications such as generative models, but also deep reinforcement learning. And the final section is really coming from the perspective of a deep learning engineer, so productionizing PyTorch models, but also coming from the perspective of utilizing the PyTorch ecosystem, so using libraries such as Caption for interpretability, or some AutoML libraries, and also Fast AI for rapid prototyping. So just to give a glimpse of what like some of the chapters have in them. So when we are overviewing the deep learning concepts, the book discusses layers, activations, losses, just to have a quick recap. And then there is an end-to-end exercise-based chapter about image caption generator. So image caption generator is always a model that involves the CNN component for image processing, but also the LSTM component for generating the the text. So this is like a good example for overviewing deep learning, and all of this is done using PyTorch. So this intends to give a holistic coverage of the language. And in the second section, first we go deep into the CNN architectures, the evolution. So we discuss right from the beginning of when the first convnets arrived all the way to efficient nets. We go into the details of these architectures and implement them using PyTorch. Similarly, in the next chapter, we go for RNNs in a similar vein, going through the evolution of RNNs into LSTMs and so on. And finally, there is a chapter on other advanced architectures with a special section on transformers, again using PyTorch to code transformers. The third section, as I said, is really focused on applications. So we'll begin with applications such as music generation or text generation. So as you can see in this figure, this is like a beam search generation algorithm using a transformer-based model. Then there is a chapter on neural style transfer, where we intend to transfer a style of one image and the content of another image into a third image altogether, as you can see in the diagram. There is then a chapter on GANs with a specific focus on deep convolutional GANs. So in this image, you can see a UNet architecture is being used as a generator for pix-to-pix architecture, actually. So again, using how do we use PyTorch to efficiently code GANs? And then finally, the chapter on deep reinforcement learning basically has an end-to-end example of training a Pong video game agent. And it goes through the life cycle of how we can make incremental improvements going from a simple Q network model to a DQN model coding in PyTorch. And finally, the last section of the book, which is focused on engineering, first goes through the different ways of productionizing PyTorch models. There is a lot of like exercises around scripting, using Torch script to make the models readable in C++ and so on. Also, there is a section on being able to use PyTorch in the cloud, in the different cloud platforms such as AWS and Google Cloud. Then there is a specific chapter for distributed training, just to make sure that we make the best out of our hardware while training or even evaluating our models. Then there are, like, the last 3 chapters of this book are really focused on the PyTorch ecosystem. So first up, there is this AutoML with PyTorch. So think of neural architecture search or just hyperparameter search. So there is a library called Optuna, which can be used with PyTorch very efficiently to do these kind of tasks. And similarly, there is a chapter specifically on interpretability. So there is a very well-written library called Caption, which can be used with PyTorch once again to interpret. So this is an example of an MNIST model, and it's trying to look at what the different layers of the convolutional network are really focusing on in the image. And the last chapter is about rapid prototyping. So using libraries such as FastAI or PyTorch Lightning to be able to quickly prototype and experiment different deep learning models in very few lines of code and using relatively less amount of time. So I think that's like a quick overview, more or less, of what this book really contains. But before I wrap up, I just wanted to give a feel of how the exercises are laid out. So I'm going to refer to the first chapter exercise and gonna just run through a quick notebook. The notebook is a very simple task. It's basically the classic MNIST classification task, but basically what we do in the exercises is we go through these steps of defining a convolutional architecture, as you can see, with the initialization and the defining the forward pass of the model with the convolutional and the fully connected layers. And then we define the training and the testing routines. So the routine basically is all about iterating through a data set, and in each iteration, in each batch, we get the predictions, we compute the loss, and we back propagate the loss. So all of these steps are explained in the book, like what do these lines of code mean, and we also print after every certain number of batches what the progress or what the training loss looks like. And similarly, you have some testing routine, which is very similar to the training routine, but performed on the test data set, and there is no back propagation going on here, obviously. there is then, so after we define the model, define the training and testing routines, we also actually load the data set, and we define the optimization, which is, in this case, it could be Adam, it could be SGD, but I just use ADA delta here. And this is something to be experimented upon. And after that, you just begin training the model. And as I said, after a few hundred batches, which is 3,200 data samples in this case, you keep noticing the progress of training. While it is training for us, I can just quickly show you how in the book this looks like. So as I said, it goes through the different steps. It explains why we are defining a certain model architecture, how are we doing that according to the diagram with the explanations, and then we define the training and the testing routines, going through the data loading procedure. And after defining the optimizer, we go through the training and actual model training and testing loops. So as you will see, the model trains for 2 epochs here just for demonstration purposes. And after the first epoch ends, there is the testing routine, which is being called on the entire test data set of 10,000 samples in this case. And you see that the model actually performs relatively well, 98.28%. And the training loss goes down from the starting point of 2.3 to 0.02. It is still fluctuating a bit, but that is more or less expected during model training. And the same process is repeated for the second epoch, wherein the model is trained over the 60,000 training data samples, and the training loss is expected to reduce. And at the end of the model training epoch, we again compute the results on the test data set. So as you will see, there is a slight improvement from 98.28% to 98.5%, but that's not even the point. The point is, the goal of this exercise is to explain how do we go from how do we actually perform the entire end-to-end deep learning, machine learning modeling using Pytorch in the various steps. Once we have finished the model training loop, the last step is to actually use the trained model and perform some inferences. So I'm going to use a test data point which has a digit 7, and we are going to first run the model prediction and compare it with the actual ground truth. So in this case, it supposedly, it apparently comes out to be a correct prediction, and we could play around with more of such data samples, and we would hopefully see most of the time the predictions being correct, given that the accuracy is 98.5. So yeah, this was just to give you an idea of how the exercises in the book look like. As I said, it's a very applied book in nature. So every chapter has at least one and even more exercises. And the goal of the book is really to make people hands-on by using Pytorch for different kinds of applications. And with that, I would just say that the Mastering Pytorch book is available on Amazon. So yeah, that would be it from my side.
All right. Thanks, Ashish, for the presentation on Pytorch. We have a few questions from the audience already. And let me project the first one from Edmund. He asks hey, why did you choose Pytorch as opposed to other ML frameworks like TensorFlow or Keras, which is mostly said to be relatively simpler? I guess that's a contentious statement, but I'm curious to know what your opinion is.
Yeah, happy to answer that. So actually, Pytorch is amongst the first deep learning frameworks which came up with the eager execution framework, and as opposed to TensorFlow 1.0, which had the deferred execution where the computations are performed after the entire deep learning graph is computed, which got changed after TensorFlow 2.0. So that is always one point of contention between Pytorch and TensorFlow. The second point was Pytorch is really more performant in terms of hardware usage, especially when it comes to GPU and especially when it comes to sequence models. So those were a few of reasons why I would personally choose Pytorch more than TensorFlow in my working experience. And that was the reason why I chose to write the book on Pytorch. But really, to be honest, my goal was to make the book applied in nature. So I might as well could have used the, TensorFlow as my medium. So the Pytorch is really just a medium to show how we can actually do deep learning. We could even use TensorFlow 2.0 for doing that. Regarding the ease of use, I personally find Pytorch's APIs more convenient, and it's more Pythonic, as it's always being said. So you can more easily debug your code because of that, as opposed to TensorFlow. But I also admit that ever since TensorFlow has taken Keras in their 2.0 API, it's also becoming more and more slick. So yeah, it's a very healthy competition between these two frameworks, in my opinion. And I just chose it because I happen to use PyTorch more in my work.
All right, cool. Next question is from Istvan. We all know the success stories of deep learning in image detection and NLP. In your experience over the years, what applications of deep learning have surprised you beyond those classical examples?
That's actually a very good question. So to me, like reinforcement learning examples come to mind immediately, because I have also been using now in my work a lot of reinforcement learning to do even simpler tasks, thanks to like a lot of simpler APIs that are available. And besides just the classical, computer vision or NLP classification of tasks, there's a lot of hybridization that's happening. So think of using CNNs for audio, like in wavenets, or think of using transformers, which is not a recurrent model by design, for sequential data. So a lot of hybrid approaches are coming in. There is also a lot of development in neural architectural search. So what I mean to say is, it's no more. It's getting to a point where we are not defining what kind of layers do we want. We are just letting the system figure out itself what kind of layers are the most optimal. So I'm really curious about these kind of developments, which are meta, which are going beyond just like these two classifications of image classifier or object detection for computer vision, and sentiment analysis or text classification for natural language processing. So it's going a bit more abstract than that, and that's a very really exciting development, in my opinion.
All right, cool. And then a question from probably an ex-colleague of yours, I'm not sure actually, from Lien. How much time would you say you spent writing each of the chapters? Lien, is that a question because you have ambitions as well to write a book? Did you feel like you learned something while writing the book as well? I'm curious about that one.
So Lien is indeed an ex-colleague, and hello to Lien, and a dear friend of mine. So that's actually a good question. So each of the book chapters, I would say it really varied, because some chapters were long, some were short. But on average, each chapter took 3 weeks to write. But that was just the first draft. You always have to remember that the reviews keep coming back to you. So that's something I learned along the way, and the hard way, to be honest, that it's not just the first draft you write. You have to keep getting back like requests to review, and sometimes the reviews could be like drastic, like half the chapter needs to be rewritten. So it really depends, but I would say 1 month kind of time is reasonable to expect for each chapter. And there was a second part to the question as well, Chris.
Yeah, just a sec, I'll bring it back. Did you learn something, or did you feel like you learned something while writing the book? Yeah.
That's another excellent question. So I have to again admit, I learned actually a lot while writing. So what happens is, while you're writing a book, you have to be really, really sure about what you are writing, because once it's there, it's there. So you have to do plenty of research. So on the topics where I am already quite confident, I solidified my understanding by reading more. But there were topics which were required by the publisher, let's say, that they must be there, and which were not my areas of strength. Then that's where I had to actually go and study loads of blogs, loads of articles, loads of literature, and actually learn lots of new stuff while writing the book. So that's 100% a fact that if nothing, you learn a lot while writing a book. Yeah.
All right, cool. Well, I have one last question myself, and it might be a question coming from ignorance, right? So tell me if I say something stupid, but I'm more on the engineering side of data, and when we come in contact with deep learning solutions or use cases that use deep learning frameworks, more often than not, what we see, they don't even use GPUs. So it's a relatively small data problem that can run on relatively standard hardware, I would say. If you see such a solution in real life, do you say like, you're an idiot, you should have written that in sklearn or something, is much easier? Or is there a place for deep learning solutions for, let's say, modest scale data that don't need GPU or massive compute power?
So yeah, if I understood your question correctly, yes, there are so many problems where it's a small data problem, but just because the nature of data is such that it's not inherently structured. Let's say it's not even tabular data. We are talking about images. Most of our sklearn based algorithms will fail mostly. So we will need to use some kind of a deep learning approach in many of such cases. That's where deep learning actually comes to shine. And I agree that there is kind of a fear associated with, oh, I have to use now TensorFlow or Pytorch, and that's like a lot of verbose code lying around. But that is where one of the chapters in the book is about rapid prototyping in Pytorch, and I can only suggest you to actually go through that chapter. It has a section on fast AI, which aims to make it so so short, like the number of lines of code you need to even put together a complex model is like less than 50 for sure. So it really makes it look more like sklearn than the old TensorFlow style. So it really is very inviting in terms of being able to code even small data problems, even small problems using deep learning. And about the GPUs, it is really up to our own wisdom. So if we see that there is a advantage of using GPUs, then we must, and it really pays off for the large models, extremely complex models. But for small scale, I don't think that's the biggest concern one must have, whether to use GPU or not.
All right, thanks.
Yeah.
In the meantime, a few extra questions have popped up and we have some time left. So if you don't mind, I'm going to keep on firing questions at you. Le Q Duong, sorry, man, if I butcher your name, my apologies. But what is the prospect of using Pytorch in classical numerical simulation tasks, something like solving ODE?
That's an excellent question. And so a bit of trivia, Pytorch is actually, it came from Torch, which is supposed to be actually a numerical, it was written in Lua, that scripting language, which was supposed to solve ODEs and numerical computation problems. So I am pretty sure, although I'm not an expert in that particularly, but I am pretty sure that one must be able to use tensors, the APIs that Pytorch provides to be able to solve ODEs. I'm 100% sure about that, because ultimately even deep learning is just a computational graph, and I believe you can also pose the ODE equations in matrices form, in the form of a computational graph. So it's just a matter of looking it up. I am not an expert on this, but I know conceptually that it's possible to do it with Pytorch.
All right, cool. There was one more from Ashok Tak. He says, hey, great presentation. I'm loving this book. What do you think about ML ops tools along with Pytorch? I'm actually interested in that one as well. So good question.
Yes. For this one, again, I really strongly encourage to visit pytorch.org/ecosystem. So Pytorch has a lot of evolving toolkits around the library itself. So some of the examples I have already discussed in the book, but it's impossible to cover all of them. So there is a lot of ML flow kind of tools, if Ashok means those kind of tools around managing experiments. There is a lot of tools around auto ML, which is one of them I have shared in the book as well, which is called Optuna. It will be impossible for me to spell them out here, but I can only assure you that there is a very rich ecosystem of tools around Pytorch, and just visit pytorch.org/ecosystem and you should be able to get hopefully the tool around what you're working on, because I'm talking about at least 20 to 30 rich set of libraries already in place.
All right, cool. People are really using this moment to extract all the knowledge from you, right? So I hope you don't mind. So, but here's another one from Carlos. He He says, "Hi Ashish, thanks for the PowerPoint. I know it's a bit off topic, but do you have any suggestions for learning Pyro, which uses Pytorch besides its documentation?"
Yes, I think Pyro is one of those which I just mentioned in the PyTorch ecosystem. I did not add it in, did not consider it for the book because there were already some other similar libraries that we have discussed in the book. I am pretty sure about the documentation of Pyro. I think they have well-written documentation because when I was researching for the book, I did go through Pyro, and I actually tried out some of their examples, and it does work. Unlike many GitHub projects, which really, what I'm talking about, they break at some point. But I have experience of working with Pyro, and I can assure it works. It's just a matter of looking into the documentation and also looking into pytorch.org, because they also might have an example with Pyro.
All right, cool. I think with that we can wrap up. If people have more questions, I mean, keep them coming in the comments, and maybe Ashish is kind enough to answer them on YouTube. But I would say best of luck with your book. It's a great accomplishment. Congratulations on publishing it in the first place. It's interesting to see also the journey, that it's not just about, I have something in my head, let me do a V1, send it over, do some typo checks, and then publish. No, it's it's a lot of iterations, I've learned. So I have zero ambitions to do that ever.
Yeah. One last, on a lighter note, writing, if you're doing it for making money, please don't do it.
Yeah, Lynn, that's a tip for you. So I don't know what your motives are here, but if you're maybe wanting to write a book, because here Lynn said maybe. So if you maybe want to write a book, maybe consider not getting rich out of it, I guess. I've heard it from others, by the way, but I guess it's, well, besides just being intellectually satisfying, it also puts you on the map, right? So if I want to master PyTorch, that's the guy, right? Because he wrote the book on mastering PyTorch, so it's pretty cool. I mean, again, super cool. Best of luck with the book, and thanks for showing up here at Data Science Leuven and share all your knowledge with the community. Thank you very much, Ashish.
Thank you, Chris.
All right. Last but not least, we have Gaetan back from DataCamp. This time, Gaetan, you're the least academic of them, right? Because you're actually going to show something hands-on, which probably the highest likelihood that I will understand. I actually already have a question in mind for you, but I'll first let you do your presentation to the rest of the group. But from what I've gathered, the people at DataCamp have been so kind to open source a new framework that makes their data scientists more productive, and you're going to dive in what that is and how the world can use it, I guess.
Yes, thanks a lot, Chris. So indeed, this presentation will be a bit less on the data science side, more maybe on the data engineering side, though I hope that the framework that I'll present will or might help data scientists be more efficient. So I'm going to present a framework that we built internally a few years ago, and that, at least in our case, helped our data scientists focus on data science. And by that I mean by creating materialized views or views in a data warehouse, and eventually a data model as well. But we will see in the presentation what do I mean by that. Just quickly about me, I've studied computer science, and then I spent a few years working with robots and how to interact with robots. And after that, I've joined the data engineering world, which I love. So before diving in ViewFlow, I'd like to take a step back and provide some context about why we created ViewFlow and why we needed to create ViewFlow. So I'll start by presenting the extract, load, and transform approach that we use at DataCamp in our data flow. Then I'll focus a bit more on the transformation step of the ELT approach, which stands for extract, load, and transform. and then why and how ViewFlow helps our data science team to be more efficient, and what kind of problem does it solve. And I'll conclude the presentation with a few additional notes. So just a bit more, some context around the data pipeline or the data flow at DataCamp. So as I said, we are following the extract, load, and transform approach. And to do that, we are using Fivetran for the extract and load phase. So what Fivetran does is to extract the data from from data sources and load this data to a central data warehouse, which is in our case is Redshift. The data sources can be anything in DataCamp's databases. So any data that the application produces can be extracted and is actually extracted by Fivetran and loaded, so copied to Redshift. But not only internal data is loaded to Redshift, but also our external data are copied to Redshift as well. I've just put some examples here, like Zuora and Salesforce. Just some examples. So when Fivetran has extracted and loaded the data in Redshift, so in a central data warehouse, the data is still in the raw format, and you can't really do any analysis, and you can't really retrieve any business insights from the raw data. So the third step is to transform the data. Once you've transformed the data, you can retrieve business insights and take business decisions based on that transformed data. And internally, we are using, or the data scientists are using SQL, Python, and R to transform the data. And depending on the use case and depending on their familiarity with the language. So we don't want to restrict our data scientists to use only SQL or only Python to transform the data. Once the data is transformed, that's where the fun starts, at least for the business. They can query the data in Redshift, the transformed data, to retrieve business values. And they can do that by using Metabase, which is an online tool to issue queries and to produce dashboards. They can query the transformed data that we call views in Python, in R, and the transformed data is also used in our company dashboards. So I've just mentioned it, the results of the transformation. We called it internally materialized views, or just simply views. And they are the results of complex data manipulations. So it can be aggregations, it can be joins between huge tables. We have a few tables with a few billions of rows. And it can be also the results of complex manipulation between tables from the raw data tables and also other materialized views. Once the transformation pipeline is done, we have this set of views which creates a data model, and that is considered as the source of truth for anything data for our users at DataCamp. So we've seen that Fivetran copies the raw data from the sources to a single destination. It does that very well. It does that automatically on an hourly basis. But we have the raw data, and we have to kick off the transformations that our data scientists have written. Fivetran doesn't do that, or at least not the way we want. And to kick off this transformation on the right time, in the right order, we are using Apache Airflow. Apache Airflow is a Python-based framework that orchestrates that allows us to run different tasks in Python. The core concept of Airflow is a DAG, which is a direct acyclic graph that is composed by nodes or in Airflow tasks. In these examples on the right-hand side, we have a 4-task DAG with the 4 dependencies. So we have B and C that depends on A, and D that depends on B and C. So B and C will run in parallel when A has completed, and D will run when B and C have completed. I'm not going to go too deep into how Airflow works, how the Airflow API works, but I just would like you to have the feeling of what does it take, how does it look like to write an Airflow DAG in Airflow. So to produce these simple 4-task DAG, you will first start by defining with the Airflow API your DAG. What's your DAG name? Who's the owner? When should it run? What's the frequency? So that's the definition of the DAG. Once you define your DAG, you will instantiate the tasks. And in Python, the instantiation of a task is called an operator. An operator is a Python object that will execute the code of the task. So in this case, we have instantiated 4 operators that do nothing, but that's just for the example. And once we've defined the tasks, we have to define the dependencies. It's a graph. So the tasks depends on other tasks. And in this case, we have B and C depending on A and D depending on B and C. Again, understanding the code is not important, but I just want you to feel how and understand how it looks like. We have almost 20 DAGs at DataCamp that produce views, almost more than 500 views actually. We've separated our DAGs more or less per business unit, so we try to be coherent. And so, for instance, we have 1 or more DAGs for marketing and 1 or more DAGs for finance. And the views, we can separate the views into in technical views and what we call end user views. Technical views are really more for the data scientists to organize their code and the flow to end up creating end user views, which contain really the data that will hopefully produce business values. So let's take an example on one of our DAG, the finance DAG. So this is like a DAG that is running every day. It's not just an example. This is really running in production. And as you can see, it can be quite complex for 2 reasons. First, there can be quite a lot of tasks. We have also in this example, there's a fair amount of tasks, but we have also other DAGs with even more tasks. The second reason why it can be quite complex is because of the dependencies between the tasks. We can separate these dependencies into internal dependencies and external dependencies. An internal dependency is for a task that depends on another task within the same DAG. And an external dependency is when a task depends on one or more tasks that belong to another DAG. And that's materialized here, or that's shown here in the DAG by the dark background rectangle in this DAG. So each of these rectangles here, except the dark background tasks, produce they all produce a view in our data warehouse. So you can imagine, if you remember the code that I showed you to produce these 4 task DAG, you can imagine that it might become quite complex to create or maintain a DAG like that, right? What would the steps look like? First, the data scientist should start by writing the code that produces the view. So in SQL or R or Python, so the content of the task, what the task will execute. Then the data scientist should, update the Python script that defines the DAG and add the right airflow operators, instantiate the airflow operators in there, and then finally, and even more importantly, they should define the dependencies between the tasks. Just a second example, so I'm sure that you understand how complex it might be to maintain these types of DAGs if you are using only a static approach to produce a DAG like that. To produce the DAG on the right-hand side, there's almost more than 300 lines of codes. I'm a bit cheating because I could use the Python. I could use some Python function to make it a little bit more automatic, but still, at the end of the day, the dependencies should be defined, and that's, in my opinion, where bugs could come up, and it's also time consuming. If you look at these three steps here, you can say that only the first one actually produces business values, right? The rest is just data engineering or engineering work that doesn't produce any value to the business. And that's why we decided to create ViewFlow. So ViewFlow helps the data scientist to focus only on data science. And it does that because it handles the creation of the DAGs, it handles the creation of the tasks, and it also manages automatically the task dependencies, be it internal or externals. And it does that by being relatively smart, and I'm not talking about machine learning here, but it actually analyzes or parses the SQL query, for instance, or the Python script to retrieve the tasks that could be or that are dependencies. So let's take an example here. If a data scientist wants to create a new view based on a SQL query, the only thing that the data scientist should do is to create a new SQL file, write the SQL query that creates the view. They should add some metadata on the top of the file in the header, just like the owner, who's the owner of the task, what's the description of the task, of the view, what are the columns that the view has. So some simple metadata, and then, as I said, just write the queries and the query, and that's it. ViewFlow handles the rest. ViewFlow creates the DAGs. ViewFlow creates the task, and even more importantly, I would say, ViewFlow manages the dependencies. So to summarize, what would be the view flow when we want to create a new DAG? Well, we create a new directory with a config file, which would provide some parameters for like when should the DAG starts, who's the owner of the DAG. Then the data scientist creates a new SQL or Python or R file. They write the code, they commit and push the code to Git, and that's it. Viewflow creates the DAG in Airflow. So based on our experience, we saw that Viewflow had quite some interesting and important impacts on the data team. One of the first is the quality of life for data scientists, because Viewflow supports different languages. They can use the language they are the more familiar with to create a task. It reduces context switching in the sense that they don't have to move from data science to data engineering. They just focus on data engineering, on data science, and they don't have to think about any data engineering tasks whatsoever. And a consequence of that is that it increases their velocity, because all the time they don't spend on writing data engineering code, they can allocate that time to create new views, and so new business values, new business insights. So I will conclude with some additional notes. We've been using Viewflow at DataCamp for a few years now in production, and we have even seen non-data scientists using Viewflow and creating new views, even though they didn't even know what Airflow is or how Airflow works. They just wanted a new table and a new view in the data warehouse. And they were able to create that in very efficiently and easily. We've released Viewflow recently in open source. It's on GitHub. You can have a look at the code. There's also a Docker-based demo, so please try it. Provide your feedback. We are also very happy to receive PRs. And final note, currently the open source version for some reasons only support Python and SQL. We use an internal version that supports or that includes R. That's mainly because we need to clean up the code, but we will soon include R in the open source version. And hopefully by the end of the summer, there will be only an open source version, no internal version. So we will be using the open source and continue, obviously, maintaining the open source version of Viewflow as well. And that's where my presentation ends.
All right, Gaetan, thank you very much for, well, one, for giving this presentation and sharing what you've done, and also for contributing Viewflow to open source, right? Because it's always, I see it often that companies internally build a lot of cool tooling, but then they can never open source it, or they have to go through so much paperwork that they just are not bothered. But I mean, it's nice that you guys are contributing back the work that has helped your internal data scientists, right? So probably it also helps data scientists at other organizations. As with the other questions, we're going to wait a bit until the first questions come in, because there's some delay on the line, and that gives me the opportunity to ask the first question. You probably heard of the tool called DBT, Data Build Tool, which to me, from a distance, seems very similar, as in you can write SQL code, it will transform to a DAG behind the scenes. You could use Airflow, you don't have to use Airflow. Have you considered DBT, and if so, why did you choose to continue with Viewflow and not switch to DBT?
Yeah, that's an excellent question, and you are perfectly right. DBT is definitely an alternative to ViewFlow, and that doesn't require Airflow neither. I would say we've considered DBT. When we started developing ViewFlow, I think that DBT was not there yet or in a very early stage. But I would say that the reason we didn't choose to use DBT is because DBT supports SQL only. And it's really important for the team to be able to create their views in R and Python as well. We had and we have world-class R programmers, and it would be sad that we would force them to use SQL, whereas they could be much more productive using R. So we need internally, or at least that's what we believe, to support R and Python for the team. So that's why we didn't use DBT. I wouldn't sell ViewFlow as a DBT competitor, and that, at least that's not my view. DBT, I think, is way better than ViewFlow if your workflow is SQL only. And so I would even recommend you using DBT if you are using SQL only. They have test integrations, they have integrations with other tools, and there's a big community around DBT. So I'm not selling ViewFlow as a DBT competitor, just as a tool that might be useful for you and for your data team if you are using R and Python, and if you are using Airflow.
Yeah, no, and by the way, I second everything what you say here. What we also see in reality is that it's just some users are better and more productive writing SQL, and some users are more productive writing R or Python. And it used to be that there was a whole lot of holy wars going on, like, no, this is the best tool or this is the best tool. But I think the world, or at least us data engineers, are maturing, if you will, and saying like, hey, you know what, use the tool that works best for you, right? And if I can imagine at a company like DataCamp, it is a combination of Python, R, and SQL, right? And you have to provide a service or technology that can serve all those needs, right?
Indeed, yeah.
Okay, well, there's still no questions, so I'm going to abuse the time. We have to ask some more questions. I'm curious about the Python run, though, because you can write. I looked in the documentation while you were talking, so you can write some more or less arbitrary Python code. You have to return a data frame, and then that data frame becomes your view, right? Is that code, where is that run then? Is that run on the Airflow server, or do you wrap that in a Docker container and run it somewhere else, or what do you do?
Yeah, so ideally it should be the code that executes the data processing should be executed externally, or at least on an external cluster or computer than Airflow. We haven't implemented that, so it's currently the Python code, at least, is currently running on the machine Airflow runs, or on the cluster Airflow runs. In our case at DataCamp, we are using Kubernetes, so it's instantiating a Kubernetes pod to execute the code. The R views from our internal version, the workload is offloaded to Fargate in AWS. So that's good to some extent, but that's one of the reasons why we haven't shipped the R views in ViewFlow, because it's really tied to AWS, and we want to we would like to be a bit more generic about that. So we will work on extending or improving ViewFlow to be able to run these Python and R tasks on an external cluster indeed. But that's not yet the case.
All right, cool. There's a question from Edmund. He says, hey, is ViewFlow dependent on ELT, or does it also work well on ETL architecture?
I would say that it's more the ELT approach, because it expects, at least currently, it expects the data to be in the same, the source to be in the same data warehouse or the same database as the destination. So you can't really, but it's a good question, because this is something we might think about, but you can't really have external sources or different databases as data sources in ViewFlow yet.
Yeah, got it. All right. With that, Gaetan, thank you very much for this talk on ViewFlow. And so for the audience, check it out. I'll actually post a link on the chat. I'm going to do it right now. If you want to find out more about ViewFlow, it's on GitHub. So try it out. If you want to contribute back, that would be even better. I'm going to bring the other speakers back into the screen as well. So Ashish, you're there. Quinn, I'm not sure if you're still there. There you are. Hi. Yeah, you have to root for your colleague, right? So you can't disappear when Gaetan is talking. Yeah. No. So I don't know if any of you have some final thoughts. Quinn, there were a few more questions for you, but because we're like more or less at the end of the presentation today, I propose that you either take it up offline with them if you want to, or on YouTube, or just let them find you if you will.
I replied in the comments.
All right, cool. Then to all three of you, thank you for closing this final Data Science Leuven meetup of this season. It shows, by the way, that having being in Corona times is also positive, because we can invite people from all over the world, and it only enriches our meetup. So thank you very much for contributing, and I hope to see you, all three of you, hopefully one day in Leuven as well, over some beers or other drinks. Thank you all for joining us.
Thank you, Chris.
Bye, guys.
Thanks, Chris.